On behalf of the Graduate Council, it is my very great pleasure to welcome you today to the first of the Hitchcock Lectures given by Stephen Hawking, Lucasian Professor of Mathematics at Cambridge University. The Hitchcock Professorship is one of the earliest endowments at the University of California at Berkeley. It was developed from a bequest of property made in 1885 by Dr. Charles M. Hitchcock, a San Francisco physician with a long interest in education. As stated in his will, the purpose of his bequest was to establish a professorship at the University of California for free lectures upon scientific and practical subjects, but not for the advantage of any religious sect nor upon political subjects. The fund was allowed to accumulate until 1909, when the Hitchcock Lectures were instituted with the inaugural lecture by the distinguished chemist from the University of Chicago, Julius Stieglitz. The university received an additional gift in 1930 from Dr. Hitchcock's daughter, Mrs. Lily Hitchcock Coit, best known as the donator of funds to build Coit Tower in San Francisco. Mrs. Coit directed that the professorship made possible by this enlarged endowment be designated the Charles M. and Martha Hitchcock Professorship in memory of her father and mother. How extensively this endowment has enabled the faculty, staff, and students of the university, and the general public as well, to become closely acquainted with distinguished scholars from throughout the academic world is indicated by the listing of those who have been Hitchcock lecturers and Hitchcock professors in the program brochure you have received. We are indeed proud to see the long tradition of the Hitchcock Professorship so eminently upheld by a scholar of the stature of Stephen Hawking. Professor Hawking has been described as one of the world's most distinguished astronomers and physicists working in the field of relativistic cosmology, and gravitational physics. While a graduate student at Cambridge, he and Roger Penrose, now a professor at Oxford, developed new mathematical techniques to prove the existence of infinitely dense but dimensionless singularities. During postgraduate research, he developed his singularity theorems of the universe. Hawking then applied the methods he used in these theorems to investigate black holes, showing that when black holes swallow matter, they can only get bigger. They could never fission into two black holes, for example. In 1974, he turned his attention to little black holes that might have been formed during the creation of the universe. The scale of these mini black holes requires analysis using quantum mechanics. To his surprise, Hawking deduced that at the quantum mechanical level, many black holes emit particles and radiation, now known as Hawking radiation, and they could lose mass and eventually even evaporate. So in his first 10 years of research, he developed two important but apparently contradictory ways of looking at black holes. However, as Hawking quickly realized, this apparent contradiction simply reflected two different aspects of a thermodynamic behavior of black holes, and in fact were not contradictory at all. They were the same thing in different regimes. In fact, this apparent contradiction may provide a crucial clue to a unified law that would encompass both gravity and quantum theory. And for the last 15 years, he has led the effort to quantize gravity. One result has been a proposal he made in 1983 with Jim Hartle of Santa Barbara that space and time are finite in extent but do not have any boundary or edge. If this proposal is correct, there would be no singularities and the laws of science would hold everywhere, including at the beginning of the universe. In addition to his research, Professor Hawking oversees a small number of graduate students and lectures extensively around the world. He is the author of 4 books, including A Brief History of Time, From the Big Bang to Black Holes, a non-mathematical account of cosmology, which is due out April 1 of this year. Since Professor Hawking has been suffering from amyotrophic lateral sclerosis, he will not take questions after the lecture. A press conference has been scheduled for tomorrow at 11 a.m. in Heller Lounge at the ASUC building to field questions from the media. I am now pleased to present Professor Stephen Hawking, whose first lecture is entitled The Origin of the Universe.
Can you hear me at the back? I should explain that I communicate with the help of a computer and a speech synthesizer. On the computer, I run a program written by Walt Wolters of Words Plus Incorporated. This allows me to select words from lists on the screen by pressing a switch in my hand. When I have built up a sentence, I can send it to the speech synthesizer. I can also put what I write on disk. I can then print it out. Or I can call it back and speak it sentence by sentence, like I'm doing now. The speech synthesizer I use is made by Speech Plus of Sunnyvale, California. It is by far the best I have heard. The only trouble is that it gives me an American accent. They have not yet got round to making a British version. Now for my lecture. The problem of the origin of the universe is a bit like the old question. Which came first, the chicken or the egg? In other words, what agency created the universe? And what created that agency? Or perhaps the universe, or the agency that created it, existed forever and didn't need to be created. Up to recently, scientists have tended to shy away from such questions, feeling that they belong to metaphysics or religion, rather than to science. However, in the last few years, it has emerged that the laws of science may hold even at the beginning of the universe. In that case, the universe could be self-contained and determined completely by the laws of science. The debate about whether and how the universe began has been going on throughout recorded history. Basically, there were two schools of thought. Many early traditions, and the Jewish, Christian and Islamic religions, held that the universe was created in the fairly recent past. For instance, Bishop Ussher calculated a date of 4004 BC for the creation of the universe by adding up the ages of people in the Old Testament. One fact that was used to support the idea of a recent origin was that the human race is obviously evolving in culture and technology. We remember who first performed that deed or developed this technique. Thus, the argument runs, we cannot have been around all that long. Otherwise, we would have already progressed more than we have. In fact, the biblical date for the creation is not that far off the date of the end of the last ice age, which is when modern humans seem first to have appeared. On the other hand, some people, such as the Greek philosopher Aristotle, did not like the idea that the universe had a beginning. They felt that would imply divine intervention. They preferred to believe that the universe had existed and would exist forever. Something that was eternal was more perfect than something that had to be created. they had an answer to the argument about human progress that I described. It was that there had been periodic floods or other natural disasters which repeatedly set the human race right back to the beginning. Both schools of thought held that the universe was essentially unchanging in time. Either it had been created in its present form, or it had existed forever, like it is today. This was a natural belief in those times, because human life, and indeed the whole of recorded history, are so short that the universe has not changed significantly during them. In a static, unchanging universe, the question of whether the universe has existed forever, or whether it was created at a finite time in the past, is really a matter for metaphysics or religion. Either theory could account for such a universe. Indeed, in 1781, the philosopher Immanuel Kant wrote a monumental and very obscure work, The Critique of Pure Reason. In it, he concluded that there were equally valid arguments, both for believing that the universe had a beginning, and for believing that it did not. As his title suggests, his conclusions were based simply on reason. In other words, they did not take any account of observations about the universe. After all, in an unchanging universe, what was there to observe? In the 19th century, however, evidence began to accumulate that the Earth and the rest of the universe were in fact changing with time. On the one hand, geologists realized that the formation of the rocks and the fossils in them would have taken hundreds or thousands of millions of years. This was far longer than the age of the Earth, according to the creationists. On the other hand, the German physicist, Boltzmann, discovered the so-called second law of thermodynamics. It states that the total amount of disorder in the universe, which is measured by a quantity called entropy, always increases with time. This, like the argument about human progress, suggests that the universe can have been going only for a finite time. Otherwise, the universe would by now have degenerated into a state of complete disorder, in which everything would be at the same temperature. Another difficulty with the idea of a static universe was that according to Newton's law of gravity, each star in the universe ought to be attracted towards every other star. So how could they stay at a constant distance from each other? Wouldn't they all fall together? Newton was aware of this problem about the stars attracting each other. In a letter to Richard Bentley, a leading philosopher of the time, he agreed that a finite collection of stars could not remain motionless. They would all fall together to some central point. However, he argued that an infinite collection of stars would not fall together, for there would not be any central point for them to fall to. This argument is an example of the pitfalls that one can encounter when one talks about infinite systems. By using different ways to add up the forces on each star from the infinite number of other stars in the universe, one can get different answers to the question: can they remain at constant distance from each other? We now know that the correct procedure is to consider the case of a finite region of stars. One then adds more stars, distributed roughly uniformly outside the region. A finite collection of stars will fall together. According to Newton's law of gravity, adding more stars outside the region will not stop the collapse. Thus, an infinite collection of stars cannot remain in a motionless state. If they are not moving relative to each other at one time, the attraction between them will cause them to start falling towards each other. Alternatively, they can be moving away from each other, with gravity slowing down the velocity of recession. Despite these difficulties with the idea of a static and unchanging universe, no one in the 17th, 18th, 19th or early 20th centuries suggested that the universe might be evolving with time. Newton and Einstein both missed the chance of predicting that the universe should be either contracting or expanding. One cannot really hold it against Newton, because he was 250 years before the observational discovery of the expansion of the universe. But Einstein should have known better. Yet when he formulated the general theory of relativity to reconcile Newton's theory with his own special theory of relativity, he added a so-called cosmological constant. This had a repulsive gravitational effect, which could balance the attractive effect of the matter in the universe. In this way, it was possible to have a static model of the universe. Einstein later said, "The cosmological constant was the greatest mistake of my life." That was after observations of distant galaxies by Edwin Hubble in the 1920s had shown that they were moving away from us with velocities that were roughly proportional to their distance from us. In other words, the universe is not static, as had been previously thought. It is expanding. The distance between galaxies is increasing with time. The discovery of the expansion of the universe completely changed the discussion about its origin. If you take the present motion of the galaxies and run it back in time, it seems that they should all have been on top of each other at some moment between 10 and 20,000 million years ago. At this time, which is called the Big Bang, the density of the universe and the curvature of spacetime would have been infinite. Under such conditions, all the known laws of science would break down. This is a disaster for science. It would mean that science alone could not predict how the universe began. All that science could say is that the universe is as it is now, because it was as it was then. But science could not explain why it was as it was just after the Big Bang. Not surprisingly, many scientists were unhappy with this conclusion. There were thus several attempts to avoid the Big Bang. One was the so-called steady-state theory. The idea was that, as the galaxies moved apart from each other, new galaxies would form in the spaces in between, from matter that was continually being created. The universe would have existed, and would continue to exist, forever, in more or less the same state as it is today. The steady-state model required a modification of general relativity in order that the universe should continue to expand, and new matter be created. The rate of creation needed was very low, about 1 particle per cubic kilometer per year. Thus, this would not be in conflict with observation. The theory also predicted that the average density of galaxies and similar objects should be constant, both in space and time. However, a survey of extragalactic sources of radio waves was carried out by Martin Ryle and his group at Cambridge. This showed that there were many more faint sources than strong ones. On average, one would expect that the faint sources were the more distant ones. There were thus two possibilities. Either we were in a region of the universe in which strong sources were less frequent than the average, or the density of sources was higher in the past when the light left the more distant sources. Neither of these possibilities was compatible with the prediction of the steady-state theory that the density of radio sources should be constant in space and time. The final blow to the steady-state theory was the discovery, in 1965, of a background of microwaves. These had the characteristic spectrum of radiation emitted by a hot body. Though, in this case, the term hot is hardly appropriate, since the temperature was only 2.7 degrees above absolute zero. The universe is a cold, dark place. There was no reasonable mechanism in the steady-state theory to generate microwaves with such a spectrum. The theory therefore had to be abandoned. Another idea to avoid a singularity was suggested by two Russians, Lifshitz and Kalatnikov. They said that maybe a state of infinite density would occur only if the galaxies were moving directly towards, or away from, each other. Only then would the galaxies all have met up at a single point in the past. However, one might expect that the galaxies would have had some small sideways velocities, as well as their velocity towards or away from each other. This might have made it possible for there to have been an earlier contracting phase, in which the galaxies somehow managed to avoid hitting each other. The universe might then have re-expanded, without going through a state of infinite density. When Lifshitz and Kalatnikov made their suggestion, I was a research student, looking for a problem with which to complete my PhD thesis. 2 years earlier, I had been diagnosed as having ALS, or motor neuron disease. I had been given to understand that I had only 2 or 3 years to live. In this situation, it didn't seem worth working on my PhD, because I didn't expect to finish it. However, 2 years had gone by, and I was not much worse. Moreover, I had become engaged to be married. In order to get married, I had to get a job. And in order to get a job, I needed to finish my thesis. I was interested in the question of whether there had been a Big Bang singularity, because that was crucial to an understanding of the origin of the universe. Together with Roger Penrose, I developed a new set of mathematical techniques for dealing with this and similar problems. We showed that if general relativity was correct, any reasonable model of the universe must start with a singularity. This would mean that science could predict that the universe must have had a beginning, but that it could not predict how the universe should begin. For that one would have to appeal to God. It has been interesting to watch the change in the climate of opinion on singularities. When I was a graduate student, almost no one took singularities seriously. Now, as a result of the singularity theorems, nearly everyone believes that the universe began with a singularity. In the meantime, however, I have changed my mind. I still believe that the universe had a beginning, but that it was not a singularity. The general theory of relativity is what is called a classical theory. That is, it does not take into account the fact that particles do not have precisely defined positions and velocities, but are smeared out over a small region by the uncertainty principle of quantum mechanics. This does not matter in normal situations, because the radius of curvature of spacetime is very large compared to the uncertainty in the position of a particle. However, the singularity theorems indicate that spacetime will be highly distorted, with a small radius of curvature, at the beginning of the present expansion phase of the universe. In this situation, the uncertainty principle will be very important. Thus, general relativity brings about its own downfall by predicting singularities. In order to discuss the beginning of the universe, we need a theory which combines general relativity with quantum mechanics. We do not yet know the exact form of the correct theory of quantum gravity. The best candidate we have at the moment is the theory of superstrings, but there are still a number of unresolved difficulties. However, there are certain features that we expect to be present in any viable theory. One is Einstein's idea that the effects of gravity can be represented by a spacetime that is curved or distorted by the matter and energy in it. Objects try to follow the nearest thing to a straight line in this curved space. However, because it is curved, their paths appear to be bent, as if by a gravitational field. Another element that we expect to be present in the ultimate theory is Richard Feynman's proposal that quantum theory can be formulated as a sum over histories. In its simplest form, the idea is that a particle has every possible path, or history, in space-time. Each path or history has a probability that depends on its shape. For this idea to work, one has to consider histories that take place in imaginary time, rather than the real time in which we perceive ourselves as living. Imaginary time may sound like something out of science fiction, but it is a well-defined mathematical concept. It can be thought of as a direction of time that is at right angles to real time, in some sense. One adds up the probabilities for all the particle histories with certain properties, such as passing through certain points at certain times. One then has to extrapolate the result back to the real space-time in which we live. In the case of quantum gravity, Feynman's idea of a sum over histories would involve summing over different possible histories for the universe. That is, different curved space-times. One has to specify what class of possible curved spaces should be included in the sum over histories. The choice of this class of spaces determines what state the universe is in. If the class of curved spaces that defines the state of the universe included spaces with singularities, the probabilities of such spaces would not be determined by the theory. Instead, they would have to be assigned in some arbitrary way. What this means is that science could not predict the probabilities of such singular histories for spacetime. Thus, it could not predict how the universe should behave. However, it is possible that the universe is in a state defined by a sum that includes only non-singular curved spaces. In this case, the laws of science would determine the universe completely. One would not have to appeal to some agency external to the universe to determine how it began. In a way, the proposal that the state of the universe is determined by a sum over non-singular histories only is like the drunk looking for his key under the lamp-post. It may not be where he lost it, but it is the only place in which he might find it. Similarly, the universe may not be in the state defined by a sum over non-singular histories, but it is the only state in which science could predict how the universe should be. Please wait while I load the next section of my talk. In 1983, Jim Hartle and I proposed that the state of the universe should be given by a sum over a certain class of histories. This class consisted of curved spaces, without singularities, and which were of finite size, but which did not have boundaries or edges. They would be like the surface of the Earth, but with two more dimensions. The surface of the Earth has a finite area, but it doesn't have any singularities, boundaries, or edges. I have tested this by experiment. I went round the world, and I didn't fall off. The proposal that Hartle and I made can be paraphrased as: the boundary condition of the universe is that it has no boundary. It is only if the universe is in this no-boundary state that the laws of science, on their own, determine the probabilities of each possible history. Thus, it is only in this case that the known laws would determine how the universe should behave. If the universe is in any other state, the class of curved spaces, in the sum over histories, will include spaces with singularities. In order to determine the probabilities of such singular histories, one would have to invoke some principle other than the known laws of science. This principle would be something external to our universe. We could not deduce it from within the universe. On the other hand, if the universe is in the no-boundary state, we could, in principle, determine completely how the universe should behave, up to the limits set by the uncertainty principle. It would clearly be nice for science if the universe were in the no-boundary state. But how can we tell whether it is? The answer is that the no-boundary proposal makes definite predictions for how the universe should behave. If these predictions were not to agree with observation, we could conclude that the universe is not in the no-boundary state. Thus, the no-boundary proposal is a good scientific theory, in the sense defined by the philosopher Karl Popper. It can be falsified by observation. If the observations do not agree with the predictions, we will know that there must be singularities in the class of possible histories. However, that is about all we would know. We would not be able to calculate the probabilities of the singular histories. Thus, we would not be able to predict how the universe should behave. One might think that this unpredictability wouldn't matter too much if it occurred only at the Big Bang. After all, that was 10 or 20 billion years ago. But if predictability broke down in the very strong gravitational fields in the Big Bang, it could also break down whenever a star collapsed. This could happen several times a week in our galaxy alone. Thus, our power of prediction would be poor, even by the standards of weather forecasts. Of course, one could say that one didn't care about a breakdown in predictability that occurred in a distant star. However, in quantum theory, anything that is not actually forbidden can and will happen. Thus, if the class of possible histories includes spaces with singularities, these singularities could occur anywhere, not just at the Big Bang and in collapsing stars. This would mean that we couldn't predict anything. Conversely, the fact that we are able to predict events is experimental evidence against singularities and for the no-boundary proposal. So what does the no-boundary proposal predict for the universe? The first point to make is that because all the possible histories for the universe are finite in extent, any quantity that one uses as a measure of time will have a greatest and a least value. so the universe will have a beginning and an end. However, the beginning will not be a singularity. Instead, it will be a bit like the North Pole of the Earth. If one takes degrees of latitude on the surface of the Earth to be the analog of time, one could say that the surface of the Earth began at the North Pole. Yet the North Pole is a perfectly ordinary point on the Earth. There's nothing special about it, and the same laws hold at the North Pole as at other places on the Earth. Similarly, the event that we might choose to label as the beginning of the universe would be an ordinary point of spacetime, much like any other. The laws of science would hold at the beginning, as elsewhere. From the analogy with the surface of the Earth, one might expect that the end of the universe would be similar to the beginning, just as the North Pole is much like the South Pole. However, the North and South Poles correspond to the beginning and end of the history of the universe, in imaginary time, not the real time that we experience. If one extrapolates the results of the sum over histories, from imaginary time to real time, one finds that the beginning of the universe, in real time, can be very different from its end. It is difficult to work out the details of what the no-boundary proposal predicts for the beginning and end of the universe, for two reasons. First, we don't yet know the exact laws that govern gravity according to the uncertainty principle of quantum mechanics. Though we know the general form and many of the properties that they should have. Second, even if we knew the precise laws, we could not use them to make exact predictions. It would be far too difficult to solve the equations exactly. Nevertheless, it does seem possible to get an approximate idea of what the no-boundary condition would imply. Jonathan Halliwell and I have made such an approximate calculation. We treated the universe as a perfectly smooth and uniform background, on which there were small perturbations of density. In real time, the universe would appear to begin its expansion at a minimum radius. At first, the expansion would be what is called inflationary. That is, the universe would double in size every tiny fraction of a second, just as prices double every year in certain countries. The world record for economic inflation was probably Germany after the First World War. The price of a loaf of bread went from under a mark to millions of marks in a few months. But that is nothing compared to the inflation that seems to have occurred in the early universe. An increase in size by a factor of at least a million times in a tiny fraction of a second. Of course, that was before the present government. This inflation was a good thing, in that it produced a universe that was smooth and uniform on a large scale, and was expanding at just the critical rate to avoid recollapse. The inflation was also a good thing, in that it produced all the contents of the universe, quite literally out of nothing. When the universe was a single point, like the North Pole, it contained nothing. Yet there are now at least 10 to the 80 particles in the part of the universe that we can observe. Where did all these particles come from? The answer is that relativity and quantum mechanics allow matter to be created out of energy in the form of particle-antiparticle pairs. So, where did the energy come from to create the matter? The answer is that it was borrowed from the gravitational energy of the universe. The universe has an enormous debt of negative gravitational energy, which exactly balances the positive energy of the matter. During the inflationary period, the universe borrowed heavily from its gravitational energy to finance the creation of more matter. The result was a triumph for Reagan economics. A vigorous and expanding universe filled with material objects. The debt of gravitational energy will not have to be repaid until the end of the universe. The early universe could not have been exactly homogeneous and uniform, because that would violate the uncertainty principle of quantum mechanics. Instead, there must have been departures from uniform density. The no-boundary proposal implies that these differences in density would start off in their ground state. That is, they would be as small as possible, consistent with the uncertainty principle. However, during the inflationary expansion, they would be amplified. After the period of inflationary expansion was over, one would be left with a universe that was expanding slightly faster in some places than in others. In regions of slower expansion, the gravitational attraction of the matter would slow down the expansion still further. Eventually, the region would stop expanding and would contract to form galaxies and stars. Thus, the no-boundary proposal can account for all the complicated structure that we see around us. However, it does not make just a single prediction for the universe. Instead, it predicts a whole family of possible histories, each with its own probability. There might be a possible history in which Walter Mondale won the last presidential election, though maybe the probability is low. The no-boundary proposal has profound implications for the role of God in the affairs of the universe. It is now generally accepted that the universe evolves according to well-defined laws. These laws may have been ordained by God, but it seems that he does not intervene in the universe to break the laws. However, until recently, it was thought that these laws did not apply to the beginning of the universe. It would be up to God to wind up the clockwork and set the universe going in any way he wanted. Thus, the present state of the universe would be the result of God's choice of the initial conditions. The situation would be very different, however, if something like the no-boundary proposal were correct. In that case, the laws of physics would hold, even at the beginning of the universe. So God would not have the freedom to choose the initial conditions. Of course, God would still be free to choose the laws that the universe obeyed. However, this may not be much of a choice. There may only be a small number of laws which are self-consistent and which lead to complicated beings like ourselves who can ask the question, what is the nature of God? Even if there is only one unique set of possible laws, it is only a set of equations. What is it that breathes fire into the equations and makes a universe for them to govern? Is the ultimate unified theory so compelling that it brings about its own existence? Although science may solve the problem of how the universe began, it cannot answer the question, why does the universe bother to exist? Maybe only God can answer that. Thank you.
Thank you very much, Professor Hawking, and thank all of you for coming. Hope to see you at the next lecture.